Hello and welcome to Woven Chemistry. I'm Jean Weaver, and in this video we're going to work on decoding chemical formulae and drawing particulate drawings from those. If you haven't watched parts 1 and 2, I really recommend going back and looking at those, as those cover some foundational knowledge that's important for this video. Okay, let's look at the first series of questions. I'd like you to identify the following compounds as ionic or molecular. If it's not a compound, write Na for not applicable. So this is kind of a warm-up question getting us ready for the following questions. If you need a little hint, here's a reminder. Ionic compounds are made of a metal and a nonmetal, or they contain a polyatomic ion. Molecular compounds contain nonmetals only. And if you don't have that periodic table out, I really recommend getting it out. You certainly don't want to memorize all these elements. Get the table out to help yourselves out. Okay, pause the video and come on back when you're all done. Okay, here we go. Here are the answers. A couple of things to highlight. We can tell that 142 is an ion because of this charge. 143 is ionic. You can tell by the sodium, but hopefully you also spotted this polyatomic ion here. 146 also has a polyatomic ion. Those parentheses kind of give it away. And 147 is probably the most commonly missed problem here on the page. It sure looks like a molecular compound because all of those are nonmetals, but it really contains two polyatomic ions. Okay, so moving on, let's start drawing some pictures. Here I'd like you to draw a microlevel picture of any ionic compound among the following compounds. If it's not an ionic compound, don't draw it. And include at least 3 of the cations in your picture. Okay, so pause the video and sketch out your answers and join me when you're finished. Okay, so let's take a look at these problems. We can see that we can quickly eliminate 151. This charge tells us it's an ion, so we don't need to do that. And 152, those are both nonmetals. It's a molecular compound. We can skip that too. So we only have 2 to do. Okay, so we've got magnesium hydroxide. That's a 1:2 ratio. We need at least 3 of the cations, so we're going to have to triple that. We need to have 3 magnesiums and 6 hydroxides. Make sure that your hydroxide is in one circle. Okay, the O and the H need to be in the same circle because that functions as one entire unit. Make sure that all of these circles, all of these particles have charges on them because it's an ionic compound. And then you should be connecting these deliberately with lines. You should have lines between cations and anions. There should not be any lines connecting a cation to a cation or an anion to an anion. Negatives don't stick to negatives. Positives don't stick to positives. Now there's a lot of ways to draw this. Here's another example. Okay, and it doesn't really matter as long as you follow the points I just mentioned. Okay, moving on to 150, we see this is a 1:1 ratio. So we've got 2 polyatomic ions, so the NH4 plus 1 should be in one entire circle, NO3 minus 1 should be in another entire circle. Got to have at least 3 ammoniums, 3 nitrates, and they should be in a 1:1 ratio. And make sure that cations are connected to anions and vice versa. Okay, moving on to the next question. So this time, similarly, draw a microlevel picture of the following compounds, any kind of compound. If it's not a compound, skip it. Okay, so once again, pause the video, come on back when you're ready. Okay, so if we quickly skim through these, we can see that we should eliminate 155 because it's an ion. If we look a little deeper, we see that 153 is molecular and the other 2 are ionic. Okay, so that's going to change and determine how we draw these. Since 153 is molecular, we've got atoms stuck together. We have 2 phosphoruses and 5 oxygens in the same particle. Notice there are not any charges. There should be no charges at all. And I need 4 of the first element. Well, since it's molecular, these are separate particles, so I need to duplicate this initial particle. Now notice I haven't drawn lines connecting the P's with the O's. That's because with molecular compounds, the lines they're a little bit more informative than they are in ionic compounds, and they can indicate a single, double, or triple bond. I don't want to go into that kind of detail here. I don't want to go into Vesper theory and Lewis structures. I'm just showing that they're connected. Now there's multiple ways to connect these, especially if we're not taking into account what kind of bonds we have. So something like this might be okay as well. Okay, so now getting on to the ionic compounds, we see we have a 1:1 ratio in 154. Make sure that you have charges, that HCO3 minus 1 should all be in one circle, and make sure that cations are connected to anions. Okay, 156, a little trickier because of the numbers. Al2O3, we need at least 3 aluminums, so we're going to have to double that. We should have 4 aluminums and 6 oxides. Okay, that reduces down to the 2 to 3 ratio in the formula. Make sure that everything has a charge and a proper charge, and that cations are connected to anions and cations are not connected to cations. All right, let's move on to the last question. Draw a microlevel picture of the following ions, elements, and compounds. So everything is fair game here. Okay, I really recommend that you identify what you've got before you start drawing. Okay, but pause the video and come on back when you're finished. Okay, so here we go. Here's what we have. The first one's ionic, we can tell because of those parentheses, and we see we've got a mix of everything. Let's get going on drawing these. I like to kind of do all the ionics at once and get into that frame of thinking. So here's what those would look like. So we have a 2-to-1 ratio in the first example. We've got to double that so that we get our minimum of 3. So we've got 4 ammoniums and 2 sulfates. And in the next one, we have a 1-to-1 ratio. I went a little overboard and I made 4 cesiums and 4 fluorides. Just make sure that you've got them in the 1-to-1 ratio. Okay, now going on to 307, a molecular compound. So I'm not going to do any charges. I'm going to have 2 carbons and 6 hydrogens. Again, I'm not including lines because I don't want to indicate what kind of bond we have. All we need to know is that they're stuck together. And we need to have 2 separate particles. This particle is not touching this particle. Okay, we go on to our bromine. That's very similar. It's an element. In essence, it's kind of a molecular element. No charges here. And the ion, calcium ion, would look something like this. Now, you're not going to find calcium just floating around by itself because of its charge. It would pick up negatives. So just to kind of put this in better context, I'm going to assume that it's dissolved in water. And if it's dissolved in water, it's got to have a negative ion to balance that +2. So I'm just going to assume I've got some random -2 ion in solution with it. Now I want to show you something else to give you a little bit more information and more understanding of molecular versus ionic compounds. So these ionic compounds function as one entire unit. So if this cesium goes someplace, it takes all of them with it. Same thing over here. Where that ammonium goes, they all go. But with these molecular compounds, where this particle goes, it can go wherever it wants, and the other one can stay put. Same thing here. Same thing here. This one can go wherever it wants. Okay, so there we have it. That takes us to the end of this series. So chemical formulae, as you know, they're omnipresent in chemistry. They're all over the place. So I really hope that these series of videos have taken your existing knowledge of formulae and that I've stretched it and deepened it, linked it, and woven it. And hopefully this is going to make your current class easier as well as future classes that you take.